So we have a block of mass m on the end of a string, and it moves in a circle around a horizontal table as shown. It's not the greatest of drawings, but we deal with it. And we slowly pull through the string through the small hole, thus decreasing this radius. So this radius is going to get smaller. We want to know what's going to happen to the block. Well, if we think about the angular momentum, it's r cross p. And we know that this thing's going to have some angular momentum, and actually more importantly, the net torque will give a change of L over change of time. If you like the derivative form of it, which I actually prefer, dl dt. And this says that if we have a torque on this, it's going to change the angular momentum. Well, I look at the force that I'm pulling, and this tension force is pulling straight in. It's pulling the ball in. And it's having a distance straight out. It's r straight out, its tension force is straight in. So the torque, or the force that we pull down on the string, actually gives us a torque of 0. Which means that our angular momentum with respect to time doesn't change, or L is constant. So the angular momentum of the block remains constant. I think that is the correct answer, but let's check out. So I don't think it decreases. Let's look at the kinetic energy of the block. Well, I know that the kinetic energy for rotation is given by 1/2 I omega squared. It's very similar to the 1/2 mv squared, but I have i's and omegas. So the question is, what's happening? Well, in this case, our kinetic energy originally was 1/2 it was 1/2 m r squared omega squared. And as I pull this object inward, I will see that my k prime, my new k, is equal to 1/2 m, a smaller r, let's say it goes to half the value, and my omega is going to change as well. And as my r goes down, my omega is going to go up because of conservation of angular momentum. So what's actually going to happen is going to get 2 omega. If I go half the distance in, I go twice the speed. I omega is equal to L, so if I go half the distance in, if I decrease my moment of inertia, actually, my kinetic energy is going to increase in this. It's not going to be what I wrote down. My kinetic energy is actually going to increase because as I decreases, omega will increase, but my omega increases at a different rate than what I changes at. So what's going to happen is I'm not going to keep the same kinetic energy, and the kinetic energy is not going to change. The kinetic energy is actually going to increase in this case. So really what comes down to is the torque of this object is 0. There's no moment of inertia on this block. There is work done on the block because I pull some distance in at some force. My dot product for work does give me an increase of kinetic energy. So that's actually probably a better way to explain it. Change of kinetic energy is equal to the work energy theorem, and I know that my tension force dotted into my radius is going to be greater than 0. So that means my kinetic energy is greater than 0. So my kinetic energy will increase. And if you actually do this experiment, you can take your hand, spin it around, and clamp on and then pull through your fingers on a spinning ball of some sort. You'll actually feel that you have to pull to push to get this thing to spin around. It'll spin faster, but you can actually feel yourself putting energy into the system.